So in the last section, we were doing this thing called the disk method. And if you recall, it looked kind of like, I always liken it to like a nickel. Okay, it's a solid shape. It had some thickness. And sometimes the shape was upright. And oftentimes we would lie it over so that we could see that axis of rotation there. And so we just added up all of these slices. So we're going to do the same thing here, but we call this a washer method. So why would we call it a washer method? Well, if you think about a washer, like you might have in your garage, it actually has a hole in the center. And so I'm going to treat it like a disc, but I'm going to subtract out the hole. So let's first get a picture. So this is the line y equals x. I'm going to bound it by 0 for x equals 0, which is the y-axis, and y equal 5. So this point right here is if y equals x, this point is 5, 5. And what we're going to do is we're going to take this shaded region here and we're going to rotate it about the x-axis. So it's going to come around and it's going to come across here. So you can see that this section in the center is going to create a hole. There's no material there. So let's go ahead and draw it with that reflection. Okay, so this is a line and this is that value of 5 and this is what's being reflected. And it's going to come over here. That was a little thick, but you get the idea. So what I'm going to do is I'm going to cut this. Now, why would I cut it this way? Because it always needs to stay between the outsides. And so, because it's going this way, rotating around the x, you typically cut perpendicular to that axis of rotation. So it's cutting the x-axis, so I can see that it is a dx cut. I'm going to turn this washer, and I'm going to lie it this direction. And I can see that this is that dx. And inside, I have this space that created this idea of a washer. So this is the material around the outside here. And there's the hole. So this is the hole. You can see that there's no material that needs to be subtracted out. So what I'm going to do is I'm going to find the volume of the entire thing like it is a washer. So I'm going to call this cap R for the long radius. And so if I'm finding volume, I know it's pi cap r squared, and this is going to be thickness is dx. So in this case, I'm going to have cap r squared, which is always going to be 5 no matter where I cut. That is a length of 5. I need to square it. It's a constant for the radius. Then what I'm going to do is I'm going to subtract out the hole. And that hole has to be in dx. So I'm going to, in blue, get the hole. It's just this little radius here that always, no matter where I'm at, is going from the line y equal x to that axis. And so what we do is, and this is the hole, I'm going to label it, we call that lowercase r. And so it's pi r squared. So it's a volume that I'm taking out that doesn't exist there. So that goes from the line x to the axis of rotation, which is 0. I could have just put x there. Pi r squared, and then the thickness. So I'm going to put these two integrals together. So I'm going to have pi times 25 minus pi times x squared, the whole, and they're all in dx. So since I have a pi on both of those, I like to take the pi out. 25 minus x squared dx. And now I have to think about, where do these cuts start and stop? Looks like they start at 0 in x and they end in 5. So let's try another one. This is just 1/2 of a parabola on its side. It's bounded by 0 and 4. So it's similar to the one above, but it's got this curve. So this is the shape that I'm going to be rotating, and right now we're always rotating it about the x-axis. So you can see a form, or a hole forming right here. There's no material. So you can kind of see it's going to be this bowl shape with square outsides. So let's go ahead and graph it over here. So it's this shape here. It's going to be rotated. So it's going to form this kind of bowl shape. I'm going to cut it. I'm always cutting perpendicular to my axis of rotation. So again, I see this outside radius of being 4, because this is a line y equal 4 and not 5. And I know this point, if y is 4, x had to be 16, because y is the square root of it. So I'm going to add these washers up from 0 to 16. The outside radius, we call it the cap R radius, is that length of 4 from that line. So I'm going to go 4 squared. So pi times 4 squared is if it was a disk. But now I'm going to subtract out this whole, okay, and I'm going to call this lowercase r. And lowercase r changes. Here it wasn't quite as long, and here it's the longest it would ever be. And so I need to figure out what that is, and it always goes from the curve, which is the square root of x, to 0. So I could just go square root of x. I need to know that I square that, so it's pi r squared. And then I'm going to dx it for the width. And I know my limits of integration start here at 0, and they're going to go until 16. So this is the washer method, and it's essentially taking the outer disk, which is the material, subtracting the hole in the center.